1, 6. That was the 3. And then the 1 is the 4.5. Okay. So 57 times 6 plus 1, 343 6, just turning that into a fraction, minus 4.5, that's 52 2/3. This one here, turning it into an improper fraction, 221 times 6 plus 5, divide by 6, minus, oh, I forgot what that was. Put it in parentheses, 57 times 6 plus 1 divided by 6. $164 2/3. If I add these together, because that was my conjecture, if I add those together, 52.66666666 plus 164.666666, 217 1/3. Let's see what we get over here. Oh, why don't I ever remember that? 221 times 6 plus 5 divided by 6 minus 4.5, 217 1/3. Okay, so all this was showing is that, I guess it would be, I don't know which part, continuity maybe? That's my function, 2x plus 1 squared, and I was evaluating from 1 to 5. I can do it in one solid piece, or if I chunk it up to 1 to 3 and 3 to 5, I should get the same answer. That's all that proved for us there. Okay. Now, the last part of the notes, there's two things going on. We're talking about even and odd functions with symmetric limits. On the integral. Okay, we're going to start with odd functions first. An odd function has 180-degree rotational symmetry about the origin. So when we look, any function that has an odd exponent, like x cubed, x to the 5th, x to the 13th, anything with an odd exponent is going to be an odd function. And some of our trig functions are odd functions. The ones that are odd are sine and its reciprocal cosecant, and tangent and cotangent. Okay, so let's look at what we're talking about here and come up with some shortcuts. If I asked you to evaluate the integral from -2 to 2, okay, by symmetric limits, this is what I mean. It's the same distance away from the origin, so a number and its opposite. That's what I mean by symmetric limits. And that's the only time these shortcuts will work, is when the limits are symmetrical. If this was -1 and 2, the shortcut we come up with here is not going to work. So of x cubed dx. Okay, so let's evaluate it first, and then we'll go back and see why we're getting the answer we're getting. So just doing the power rule, I'll get x to the fourth times 1/4. Evaluate from -2 to 2. Okay. One-fourth x to the fourth. Table 2. So when I put 2 in, I get 4. When I put -2 in, I also get 4. So my integral is coming out 0. And this is what happened to me in that last one in section 5.9 here. I got a 0 and I was thrown for a loop, but I know why, and we'll see it in the next one. But anyway, I get a 0. Let's see why I'm getting an area of 0, or a 0 integral. Okay, let's take a look at the graph for y equals x cubed. X cubed. Okay, so you got that snaky graph going right through here. Well, if you take a look, I told you if I could turn this 180 degrees and it looks the same, so in other words, rotational symmetry, then it's an odd function. Well, watch when I turn this calculator upside down, it should look, take a look, it's going from upper right to lower left. When I flip it over 180 degrees, it's still upper right to lower left. So this is definitely an odd function, has that rotational symmetry. And if we look now at our area we were looking at, and we were going from -2 to 2, area under the curve, so we're talking about this area and this area. Well, if you think about it, these two areas are going to be the same amount, but here my area is coming out, I have a positive height, a positive width. So here my area is coming out positive. Over here, my heights are all negative because they're all below the x-axis. My widths are still positive because I was going to a bigger boundary minus a smaller boundary. So here the area is coming out negative, and because they're the same amounts, and they're canceling each other out. So that's what's giving me an area of 0. So anytime we have an odd function with symmetric limits, the integral is 0. So we can just zero those out and not even have to worry about them. So odd functions with symmetric limits have a 0 definite integral. So we don't even have to do those. If we see the odd functions with symmetric limits, we can just put zeros in for them. And that's what happened to me on that last one. It was a trig function. It must have been, let me see real quick what it was. I'm not going to take time. But again, if I see sine or tangent, those are odd functions also. Can't believe I didn't do one. But if we just take a, I'm not even going to bother. Those will be zeros also. I won't waste your time. Okay, now let's take a look at even functions and find our shortcut there. So our even functions have the y-axis as a line of symmetry. So you can fold them on the y-axis and get them to match. The odds, you can turn 180 and get them to match. Okay, so that's what they look like if you graph them. Any even exponent, like an x squared, x to the fourth, x to the sixth, and the trig functions that are even, our cosine and circle secant. So let's see what happens when we do, and this one's not much of a shortcut, but a little bit. From -2 to 2, so there's our symmetric limits, x to the 4th dx. All right, we'll just answer, and then we'll see what's going on. So putting in, doing the power rule, I get x to the 5th times 1/5, evaluating from -2 to 2. Let's see. 1/5 x to the 5th. And I'm good there. So I need the 2 first. That's 6.4 minus a -6.4. And you can see because I'm subtracting, I end up doubling my answer, 12.8. So let's take a look at the graph. Y equals x to the 4th. I know is that just a wider parabola from -2 to 2. So what's happening is the area is essentially divided into two pieces because it hits the origin there. And you can see these two areas are going to be identical. They have the same heights and the same width. So I get this area that's in the first quadrant here. It doubles itself when I add it to the part that's in the second quadrant. So our shortcut, it's not really much of a shortcut here for even functions, would be to evaluate, instead of using the symmetric limits, because a lot of times it's easy to put in a 0 into things and evaluate in your head, you can go from 0 to the upper boundary and then double that answer. So I'm just doing the one piece and doubling it. So that's the shortcut for evens if you want to use that shortcut. Otherwise, you just go through and do it with both boundaries there. So how do we apply this last rule? If I asked you to evaluate the integral from -3 to 3, so when you see those symmetric limits, think, boy, shortcuts, be clever. Let's go 7x cubed minus 8/9 x to the 5th plus 4x to the 6th minus sine 4x plus 6 tangent 1/2 x. Well, that don't look too bad. Dx. Okay. You could go through, because there's no outside power here, do each one of these separately. All 1, 2, 3, 4, 5 of them. Plug your both numbers in and get the answer right. But if you're clever, be clever. We know that because these are symmetric, any of the odd functions in here, the integral is 0, so I can just throw them away. So, and it's the powers you look at, not the coefficients. I probably could have put like an 8 here just to emphasize it. This is an odd function because the power is a cube, so I'm going to throw that away. That's gone. Here's another odd function. Gone. That's an even. I'm going to keep it. Sine. Sine was in the only even one is cosine and secant. This is an odd function. Throw that away. Tangent's odd. All 4 of those are going to go to 0. So now all I have left is one term to deal with. So, and if I want to use the even shortcut, I'm going to double the integral from 0 to 3 of 4x to the 6th.